All right, so welcome back. Today is the last day of new material and lecture, but we have a special guest today, Samreen. She's here to tell you about Corn Hacks, which is an annual event. Is this the fourth or the fifth one? What is it? Fifth? Okay. This is the fifth Corn Hack. I've been a judge for them for several years. I'm not the only judge, of course, but some really amazing projects to come out of it. It is basically a hackathon. Where you're given 24 hours. You can form a team, you can do it individually. I've seen plenty of people do it individually or with a team. You take it as an opportunity to learn something new and just build an app, build a game, build something over a 24-hour period. And it's on, you get a whole bunch of food, I'm sure. And there are prizes. You can win fabulous prizes. I think that the first year that I judged it, there were 4 switches, right? This is when the Switch just came out. So otherwise, there are Bluetooth speakers and a whole bunch of other things like that. So the poster is up here with some information as well as a QR code. I'll let Samreen go ahead and talk about it.
Hello everyone, I'm from the marketing committee of Corn Hacks this year. Corn Hacks is UNL's own hackathon. As Dr. Burke explained, hackathon is a social event where programmers come together to make interesting projects from scratch. So it's like a 24-hour event where you start with your team, make some project that intrigues you, and at the end it's judged by the judges at the event. This year, Corn Hacks will begin on the 21st of January, which is a Friday. The participants will meet to make their teams up. Teams are usually from 1 to 4 people. And once you have the teams formed on Saturday, 22nd of January, you start coding, and the coding session leads up until like Sunday. And at the end of the coding session on Sunday, we have the judges looking at all the projects. So really cool prizes this year worth $3,000. And we have 3 themes. The main theme is retro. As you can see on the posters, we kind of made like a retro theme this year. We also have 2 side tracks called Retro Aesthetic and Hardware. So you can make projects that fall into any of these tracks, or like something that doesn't even match these tracks but intrigues you. And the prizes are really cool. We have a lot of food. We have really cool swag. It's a great way to like know more people from the computer science or like the software engineering department, or like anyone who likes coding in general. And you get to meet a lot of good people. There'll be some workshops by our sponsors mostly. And it's a great thing to put on your resume. And if you've been thinking of making a project of your own, this is a great kickstart. You can start the project, get it somewhere, show it to people, gives you a lot of confidence, and it's a great thing to be part of. Here's the poster. There's a QR code that you can scan with the poster, and you can also follow us on Instagram. We post updates on the event. Maybe we'll show what prizes we're having and other cool, interesting stuff about the event. So we also have a website. You can go to this website and register from there. If the QR code doesn't work for you, you can see what we did in the previous years. It's a pretty cool website.
That's unlcornhacks.com. This one. There you go.
We usually have it in Johnny Carson Center, and that's where we're having it next year too. You can see pictures from last year, and there's a photo release form. It's a pretty fun event. We got really cool swag last year, which I still wear all the time. So registration is open up until next year. Here's the QR code again if you guys want to scan it. Here's the poster. We've also put up posters in Avery, and you guys can scan it from there as well. If you have any questions, you can email us. There should be an email ID, or you could reach out to me on the Outlook email. It's score7@huskers.unl.edu. You can also DM us on Instagram. We can answer any questions that you have related to the event. We're really excited to have you guys on the event, and we hope we can bring up the participation because we're working really hard to make this event a success. Thank you.
Thank you. Well, so, yeah, go ahead if you want to. I'd add that just because you've gone through one semester doesn't mean that you're not qualified to do something, do this. You have plenty of programming background already to pick up something new. You could go ahead and say, I want to learn, I don't know, Unity game development, like with the retro theme, an 8-bit side scroller, right? You could just, you could pick up the basics the day before and then start developing your own game immediately the day after, the day of. And if you've got, a team of people, then you can spread the work around, art, music, programmer, whatever, and some really cool projects have come out even from freshmen. So keep that in mind. And even if you don't, plan to win or play to win, it's still fun to be there and be there for 24 hours and get fed. And there might be, at least when I've gone and judged, there's been an abundance of leftover food, and cold pizza is just as good as warm pizza. So, all right, thank you.
Thank you so much for letting me.
Sure, and let me know about next week for the other ones.
Okay, thank you.
Okay, so our last topic, I'm going to put a pause on that for a second. What I did yesterday in the main section, because somebody had asked about threading in the main section on Monday, and I gave a short answer because I hadn't planned on talking about multi-threaded programming, but I thought that it deserved enough of a more full response and demonstration. So I threw together a quick demonstration of multi-threaded programming. So just to introduce this idea here, you've all been writing single-threaded processes, single-threaded programs, right? Where you've got a program. A program, by the way, is nothing more than a bunch of code that is being run at that time, right? Actually, that's a process. Sorry. So a program is stored on disk. When you load it up and it starts running, sometimes that's called a process. And a single-threaded process only runs on one core. It only runs on one processor at a time. It's got code, it's got data, it opens up files, it's got its own stack, right? But if you've got a multi-threaded process, that's one process, but it launches these independent threads that have their own stacks and their own registers, and they can be run on multiple processors all in parallel, right? It's parallel programming. Of course, you can do this with regular old processes. If I've got a process, I can run a process over and over and over again. For example, let's go ahead and take a look at this do nothing process. So Emacs, do nothing. .c. All right. So this process here, all it does is it starts, it prints out hello, and then it flushes the output so that it'll actually print instead of blocking. And then it goes to sleep for 10 seconds. That's what that's doing. All it's doing is it's going to sleep and then waking up 10 seconds later and saying world and then dying. Right? That gives me enough time to actually see these things in action. So GCC do nothing. Right? Obviously, if I run this, it's going to do nothing. Hello. It prints hello and then waits for 10 seconds. And then after it's done, after 10 seconds, it'll be done executing. Maybe I should have gone. There we go. World. Right? I don't know if you counted on in your head that was 10 or not, but that's what it was. I can launch as many of these as I want. 1, 2, 3, 4, 5. Right? Now, if I list out the processes, there they are. They're all running right now. They're not doing anything. They're just asleep. But they are there. And then they, of course, execute, and they're all done after 10 seconds. Each one of them individually. That's because on CSE, I've got 64 processors. Right? 64 processors that can all be running something at the same time because it's a multi-user environment. We've got hundreds of students, we've got dozens of faculty and other things, and of course, not to mention the system processes themselves that are all being run at the same time. Now, at any one time, a processor might not be all that busy, but at other times, for example, over here, somebody's taken processor 15 and they're done with it. Now it's over on 41 and it's 95% usage. Right? So if you're only using one process, that means that the work that you do is all sequential. For example, if you've got a pile of firewood, right, and you've got one axe and one person, that person has to chop the entire pile by themselves. If it takes an hour to do it, right, then it takes an hour to do it. But what if I had two people and two axes? We could split the pile in half, and now how much time would it take us, assuming that they would work at the same pace? One of them went gold brick, 30 minutes, right? Well, what if we had four people? Now it's down to 15 minutes, right? Same thing with computing. If I can split up the work, computational work, and farm it out to multiple processors, I could probably get done faster, right? So let's go ahead and take a look at another example here. Count primes. Let's see. There we go. So all this program is going to do, this is a single-threaded program still. I've got this function called isPrime, and it determines whether or not an element is, or an integer is prime. And what I'm going to do is I'm going to start a clock to count how many seconds it takes to execute this thing. And I'm going to count the number of primes from 2 all the way up to some input value. So how many primes are there from 2 to 1,000? It just goes into a simple for loop here, and if it is prime, it increments this counter, okay? So let's go ahead and take a look at how this works. This is still a single-threaded process. Oops, I need the math library. There we go. It is CSE. Let's go ahead and run it. Oh, I need to give it an n. So how many primes are there from 2 up to 1,000? Apparently 168. I've got Wolfram Alpha up open in the background here to ask to confirm that it's correct. Number of primes less than 1,000. Oh, I said 10,000 there. Should be 168. Great. All right. So my program is correct. But now what if I go up to, I don't know, 16 million? While we're waiting for that, I'll go ahead and ask Wolfram Alpha. 1, 2, 3, 1, 2, 3, 16 million. All right. I think it's about 1.3 million. Oh, 1,031,130 primes. Okay. So it won't take that long. This is usually about 10, 15 seconds on CSE. But it came up with the same answer, so we're good here. Right? Now, it took about 16 seconds here. What if I did this on 2 threads? How would I split up the work, first of all? I could say, you take the first half of the pile of firewood to chop, you take the second half of the firewood to chop, and that's how I divide the work. Here I could divide the work saying, you take numbers 2 up to 8 million, and you take numbers 8,000,001 up to 16 million. Report back to me how many primes you find in that range. You report back to me how many primes you find at that range. I'll go ahead and add those two together and report the value. So I've got a program here that does exactly that. What was it? Count primes and threaded. By the way, this is usually, I usually do this in 156H. I just adapted it to C because there was a question in the main. In fact, I do prime counting as well because I need something that is computationally intensive. I don't want it to just execute in a matter of 1 second, but I want it to do something substantial. I don't just want it to sit there and wait or sleep or something, do nothing basically. So don't worry about the details of this. What I've done here is here's count primes, and it takes a low and a high value, and then it counts the number of primes between that range, right? And then it ultimately returns the result. It doesn't return it as a regular function does, because this is all going to be asynchronous, just like the asynchronicity that we talked about with respect to graphical user interface programming, right? It's all that if I've got 4 threads here, it could be that thread 3 finishes first, then thread 1, then 4, then 2. And on a different run, it could be completely different on when they get done, depending on how much work they're actually doing and how much processor time they actually get. All right. So the inputs here are n and how many threads you want. And what I do is I create threads. They're called P threads, or the POSIX threads in C. Where do I do that? Oh, I do that down here. I split up the work up here. Sorry, this is me splitting up the work and creating the threads down here. Yep, there. I start a clock because I'm still going to time it. I create the threads through this P thread create. P is just standing for POSIX. POSIX is Portable Operating System Interface. Don't ask me what the X is for. POSIX. Unix or something maybe, I don't know. It may not stand for anything. And then I block the main thread until every other thread is done. If I create 4 threads, I can't just answer with just the first 2 values. I need all 4 values in order to sum them up to get the full value. So I join the threads together. All I'm doing is blocking the main thread, this main method, this main function here, until they're all done, so that I can add them up, stop my timer, and report the results. Okay? So again, don't worry about how to do it. If you want the code, I can post the code, and you can read all about p-threads and how to create them and how to have fun with them, whatever you want. But I'm going to go ahead and compile this now. Count primes threaded. I still need that math library, and now I'm going to need the pthread library. All right. Oops, it should be lpthread. There we go. All right. Let's run it. Of course, it's going to ask me for n. And if I do, say, 1,000 again, and I get 1 thread, that's exactly what I was doing before, 168 in a blink of an eye. But if I do 1 thread and 16 million, then I'm going to get the same exact result as I got before. Probably actually a little bit more expensive computationally, because now I'm paying for creating this additional thread beyond the main thread. It's comparable, right? 10, 15 seconds I said before, right? Now let's go ahead and up it to 2 threads. Again, the first thread here is searching 0 up to 8 million. The second thread is searching 8 million up to 16 million, right? And it got done in only 7 seconds. Remember, before it was 10 to 15, so it's roughly half now, right? Roughly, because of course you are threads don't come free. Creating them, managing them, thrashing in and out of a processor, right? Then that all takes computational time as well. So it's there are diminishing returns, right? But if you increase them, if I go up to 4, I would expect roughly half as much time as before. Right? 1, 2, 3, 4. Come on. CSE seems busy today. This is way better last time. Less second. This is actual time, by the way. The computation time stays the same. Why? Because it's adding up the computation time of all 4 processors. So yes, this one was only 6 seconds. This one was only 6 seconds, 6 seconds, 6 seconds. Add those up, and that's the actual processor time. Right? What if I go up to 8? Right? Even better. What if I go up to 16? Blazing fast now. 32? Actually, I'm just going to go up to 64. Right? Wow. Almost immediately. Why? Because I forced my program onto all 64 processors of the CSE system. Right? Now, we live in a multi-threaded environment. Right? There is nobody that creates chips anymore that are just a single processor. Duo, right? I think that this one has 8 processors or 10 or something like that. This is an i9. I don't know how many cores it has. But you know, typically I see a couple of Windows devices here. What have you got? i7. How many cores is that? You don't know? Does it say quad or does it say ocho or anything like that? Say what?
I have an i7. It's 8 cores.
8 cores. All right. And maybe with hyper-threading, you can actually get 16 processes on it. Right. I'm not sure what the hyper-threading is here. Maybe this is only 32 cores and it's actually hyper-threading or something like that. But in any case, should I go up to 128? If there are only 64 cores or 64 processes that can do this, the 64 other of them would be idle all the time. It would be like splitting up that firewood again and having 128 people, but only 64 axes. Right? You can't. The other 64 people are just going to sit on the sidelines and do nothing because they don't have the tools to actually do anything. Let me go ahead and bump this up to 64 million. And I will run it. Actually, I'll run it like this. Oh, come on. All right, that was too fast. Obviously, the computation time is going up here, but it was still too fast. What I want to do is I want to show you what the activity on CSE looks like. I'll just go in as a different user here. And I'll use a utility called htop that I showed you before. There's all the processes that are running on CSE right now. And let's go ahead and bump this up to 128 million so that it lasts for at least a couple of seconds. All right. Hey, there we go. I'm really burning processors on at least for a couple of seconds. Maybe I kicked on a fan down there or something like that. I'm sure that if we go up even more, 256, I could get up to 1C or too far. That's a billion, right? I just want to make sure I don't have overflow here. That's 100 million, right? Okay. Let's go ahead and farm that out for a while there, and then we can really start seeing the flames coming out of the CSE server downstairs, right? Oh, there. They killed me. Why? You're not allowed to have that much processor time. I think that there is like a 10-minute limit. I exceeded that 10-minute in a matter of seconds because, again, it's counting up all 64 processors, right? So I reached the limit there. Now, if I actually wanted to do something like this, of course, I would take it over to the HCC Holland Computing Center and put it on a massive distributed computing system. And probably use different framework too, because their distributed computing systems actually go not to just processors, like they're 4 cores on a processor. It'll actually have hundreds of processors, and then you have to farm it out to each one, and you have to use it completely. You can't use threads anymore. You need to use distributed computing, and you need to use interprocess and network communication to go back and forth on all that stuff. All right. So there was my, I guess, 10-minute introduction to multi-threaded computing, or at least why you would want to do it, right? If you can get more people to chop your wood, right, then you can get more wood chopped in a shorter amount of time. Of course, it means you're still paying for the hardware, you're still paying for the computation time. It's just that it's done in parallel. All right? Questions? No? All right. So I'll go ahead and exit out of this. There we go. So the last topic is just a simple introduction to databases, and I'm not even going to go over it too in depth because, again, it's one of those extra end topics. It's not on your final or anything like that. It's not on the project even, but we do talk about it more extensively in computer science too. We go through SQL, we go through database design, we go through database connectivity using Java. And unfortunately, the Java version of your Lab 15 next week still works, so I encourage you to do it. And if you want to try the C version, it's the exact same thing, but it uses ODBC instead. It is broken on the CS50 IDE, so you would have to go to the lab to do it and use the CSE server. Or you'd have to watch video 1.3 or whatever, where I show you how to set up your environment to connect to the CSE server instead of the CS50 IDE. In any case, we've already given credit for it. You don't have to do it, but if you want some fun stuff to do, then do it, right? Data is fundamental, as you've already seen, right? That we write programs to process data, to crunch data. And in C, and Java, the 3 basic data types are going to be integers and doubles, both of them numbers, and then strings, char stars, right? And then we extended that both in C and in Java by collecting things together using encapsulation. Not everything is a single number. Not everything is a single string. A student is a first name, last name, social security number, NUID, GPA, right, et cetera, et cetera, et cetera. You want to take all that stuff and treat it as one logical unit. But what about a student's birth date? Date of birth. What did we do to model that? We did a separate class, right? In Java, we did a separate structure in C. We normalized it. We realized that this is one entity. This is a date is a different entity because it is a year, day, and month, right? And so we separated those out and normalized it to do different pieces of data. That is what a relational database management system does. That we use composition encoding. We use a database, a relational database, with respect to data storage. We also need them because programs are short-lived. Other than this one program that I just showed you that took or programs that I've showed you that are very, very inefficient, that would have taken 20 years to compute had we not done them in a different way. Most of the programs that you've written are done in a blink of an eye. They're ephemeral, right? They're short-lived. We need a way to save or persist data across multiple runs. We don't want to just open the data, process it, and be done with it. We want to save that data among different programs, among different runs of the same program, etc. And so far, we've also looked at data, but we've looked at data in various formats. CSV formats. You've seen XML formats in one of your labs, where you had to output state data to an XML. And then you may or may not have seen JSON data as well. So let's go ahead and take a look at an example here. Here, CSE books. There we go. This is data that's presented and intended for human readable consumption here. This is table data, tabular data, right? We've got various textbooks for courses. They're related to a course. There's the title of the textbook. There's the author of the textbook. There are the topics, and then there's the URL that you can get this free textbooks and free alternatives. By the way, I should update this because I think you can go to, or what's the one place that you can go for free tech? Libre? Something like that? I don't know. You can download gray books, right? That are... yeah. Well, O'Reilly, but I'm talking about the pirate sites. I forget which one it was, but it's not on here. I should put it on here. But in any case, I was avoiding saying the pirate sites because, just because. But anyway, you can go ahead and organize these, by title, by course, etc. But it's not normalized. A course is different from a book, right? It's logically a different object. An author is different from a book, right? But I've put all of these things into one row. That's led to duplication of data. You'll see that I've duplicated CSCE 155A 3 times, right? 155T here is repeated 4 times. That introduces potential failure points. For example, what if I misspelled or used different casing? Like I used under lowercase CSCE, right? Would those still be logically the same course? Well, conceptually, yes, but how do I make that association anymore? I would have to use some sort of ignores case kind of comparison. Well, what if I didn't put a space in between versus a space or 2 spaces or a tab or something like that? I need a way to solve that problem. Now, unfortunately, other ways of presenting this data are also fall short because this is what's called a flat file. It's taken this complex relational data model and it's flattened it down into one table. CSV is comma-separated value files, you still have the same problem. It's still data. It's just not it's the exact same presentation, by the way, as well. It's just that it's not very human readable anymore, right? If I come in and I change things, right? CSE, I don't put the space there. Here I go CSCE, right? Those are all potential data anomalies and leads to bad data, all right? So maybe XML is the solution. You can come up with a schema. It's called a schema. Don't worry about it. But you can come up with a schema to rigorously define this data model. But it's a little bit different in that it is hierarchical. I've got a root element here, and then I've got children elements. Here's one book. Here's another book. Here's another book, etc. But I've still presented this data as a flattened data model. I have repetition of the same course over and over and over, right? I do have a little bit better representation in that I've got these tags here, that the book stops here and it logically stops here, instead of relying on end-line characters, right? I've actually got tags to delineate these pieces of data. A course, anything between this opening tag and this closing tag is designated as the course number, right? But again, there's still no logical separation between these. Not only that, but I'm now repeating a lot more data. Rather than over here CSV, I had the header once, right? I've now repeated course over and over and over again. So I've actually blown up the size of this file. Right? JSON is JavaScript object notation, and it's a little bit more lightweight, but it's still the same problems. It's still it's a key value pair here instead of a hierarchical data. It's key value pairs. Here's the course, it's a string, and here's the value, it's also a string. These are all strings, but of course you can also have numbers, right? Number of pages, and then you can have a numerical literal over here instead. Say, there, 345, whatever. But it's still the same problem. It's a flattened data model. A relational database management system solves all those problems. There's some other disadvantages here that I didn't mention. For example, if you store everything into one file, that means that one thread or one program comes in, starts reading that file. It potentially puts a lock on that file, blocking all other programs or threads from operating on that data. Right? Not only that, so it's not multi-threaded. It's necessarily sequentially processable, et cetera, et cetera. There's no format enforcement, right? There's repetition of data. There's no integrity. I can't say that this should be a number, an integer, and only ever an integer, right? So there's no strong typing there. To find a particular record requires you to process the entire file because there's not necessarily any logical order to it. Sure, you can sort it by, say, title, but then what if I want to search by author? I would need to open it all, resort by author, and then search for the author that I want. Right? So a relational database management system solves all of these problems in that it stores data into tables. Now, for our purposes, a table can look like an Excel file. Excel is not a database management system, though. If you do a lot of work in the Microsoft environment, Microsoft Office, that is, MS Access is the database version for Office. Anyway, tables contain columns and rows, just like a spreadsheet does. The columns correspond to individual pieces of data, just like this table does over here. The rows correspond to individual records, right? Just like the tabular data over here. But a database separates these things out into separate tables and then defines relations between them. And that's where we get the word relational database management system. There are a couple of relations that you can define. You can define a one-to-many relationship. So for example, authors. What's the relationship between books and authors? Or what's one potential relationship between them? One author can have multiple books. I don't think I have any records like that. But you can have one author that authors multiple books. There's a one-to-many relationship there. From the perspective of the books, though, it is a many-to-one relation. So a one-to-many relation and a many-to-one relation are the same thing. It's just which perspective are you coming from. Right? I also see a book here that has two authors. So if somebody can write multiple books and a book can be authored by multiple authors, then we could have a many-to-many relationship, right? 4-to-4 or whatever, right? One record in a table A can relate to many records in table B, and one record in table B can relate to many records in table A. The example that we just talked about here. Let's see. Yeah, so records in an RDBMS are identified typically with what's called a primary key. Typically, you let the database generate and handle those for you. The database is very, very good at its job. Let it do its job. So it'll auto-generate these keys. But how do you relate two different records in two different tables together? You do it through usually a primary key and a foreign key relationship. All right? We'll take a look at that, what that looks like here in a second. But in any case, it provides all of these nice features here. We now have security, right? Rather than just setting a file permission for one giant file, you can read this file, or you can write this file, or you can do neither, or one or the other, or both. Now what we can do is we can have fine-grained security. That user over there is allowed access to that table over there, but not that table over there. That user is allowed access to all the tables. that user is allowed read access to any table, but they can never write anything to it, right? And you actually want to do this, especially if you've got a program that reads data and writes data. If you've got a piece of your program that is only ever loading data, give it access that it can only ever read data so that you don't make any mistakes, right? You want to limit the number of potential failure points. Data storage can now be done in a remote database server instead of on your computer or through a file share or something like that. The integrity can be enforced. If you define a column to be an integer, then the database will enforce that it is an integer. Any attempts to put something that is not an integer into that column will be rejected by the database. Those are constraints that you can define. You have multi-user parallel access because of the ACID principles. What are the ACID principles? The ACID principles are atomicity, consistency, isolation, and durability. When you interact with a database, you will either load data up from it, or you write data to it, or you do something with the database. Then you want these 4 things. It's all done inside of what's called a transaction. A transaction is an atomic unit. That's where atomicity comes in. It's an all or nothing thing. If you have a transaction that inserts 3 records, A, B, and C, A, fine, B, fine, but C, oh, that's some bad data right there. What the database will do is it'll roll back that entire transaction, like the first 2 never happened. Right? It's an all or nothing thing. That's a transaction. Of course, you could split these 3 queries up into 3 different transactions. That's how you might want to design it. But the takeaway there is that it offers this atomicity. It's either all or nothing kind of thing. It offers consistency. Before this transaction and after this transaction, all of the rules that you've defined for the database are consistent. They're unforced. All the rules will be followed with all the data in the database. All the rules will be followed in all the data in the database before and after. But during, it could interrupt those rules for efficiency purposes. But before and after, you have a guarantee on this consistency. So you can define rules and have an assurance that those rules are actually being followed with your data. You have isolation, that one transaction over here will not step on the toes of another transaction over here. They can interleave. One can be done before or completely after the other, but they basically get their own view of the database. They won't step on each other's toes. Right? You also have durability, that once a transaction is committed and goes through, it remains so. So this protects you from catastrophic error, like if somebody kicks out the power cord, right, and you bring the database back up, you will bring it back up in a consistent state. Right? If it was in the middle of a transaction, when you bring it up, it's durable. It'll be like that transaction never happened. Right? You also have CRUD, so alphabet soup, right? CRUD is the 4 basic operations for any database. You need a way to put stuff in. You need a way to take stuff out. You need a way to modify stuff that's already in there. And you need a way to remove stuff that's in there. And that's create, retrieve, update, and destroy. Right? You insert new data into the database. Data's got to get in there somehow. Right? You can retrieve it. If it goes in but it never comes out, it's kind of useless. It's just a black hole. Otherwise, you can update data that already exists in there. You modify current data. Or you can destroy. You can just remove records. Okay? Now, again, we're not going to get into the specifics of SQL until next semester. But I would draw your attention to the following game database. If you do choose to do Lab 15, this is the game database that you'll be working with. What does it model? It models your favorite video games, right? We have a game table right here. What's in that game table? What's that first one right there? It's a what? It's an ID. And what is that? I don't know if you can see it too clearly, but what is that little symbol right next to it? This is a diamond. This is, I don't know if it can I, oh, there we go. All right, it's really pixelated now, but what is it? It's supposed to be a key, a primary key. And the name of that primary key is game ID. Well, and down here I've got another ID, right, as the name implies here. It's got this, now it's got a red diamond associated with it. How does that come into play in the database here? I've got a publisher table. So a game and a publisher are completely two different entities, right? A publisher is typically a person or a company. A game is a product that they produce, that they publish. So how do I relate these two things together? I've got a publisher ID here that you can then follow back to this table, back to this publisher ID right here. So give me a game. I just did GTA 4 the GTA series yesterday. Give me a new game now.
Mario Odyssey.
Oh, okay. Oh, that's not new though. All right. So Mario Odyssey. Is that how you spell it?
Yeah.
All right. Thank you. Good. All right. Who published Mario Odyssey? Nintendo. So how would you look that up in the database? You would have a game record here, and it would have some publisher ID, maybe 1, 2, 3, 4. It would just be a number, right? Because these are integers. This is an integer. What is this thing here, as an aside? The name of the game is a varchar 255. What do you think that stands for? Well, what do you think char stands for? Character, right? So it's a string. It's a variable length character of up to 255 characters. So that's what a varchar is. Anyway, it has a name, which is Mario Odyssey, and then it has a publisher, which is 1, 2, 3, 4. I follow that relation back to the publisher table and look up the publisher with an ID of 1, 2, 3, 4, and I find that it is indeed, say, Nintendo. Right? I've separated those two out, and I've related them together. This defines a parent-child relationship here. Let me go ahead and rewrite it. I've got a publisher here, say Nintendo, right? And how many games has Nintendo published? Just one? Many, right? So I have a one-to-many relationship here. What did that look like as far as, this is called an ER diagram, an entity relation diagram. How was that relationship there represented? A many, this chicken foot here, many to one relation, right? So this is a one, and then many. Sometimes we just use M, or we use the symbol one to many, right? Kind of relationship, okay? The publisher has published many games. So game 1, game 2, game 3, game 4. Right? Look at it from a top-down view. This is a parent table, and these are the children, or parent record, I should say, and these are the children. Right? They all refer to all the games that they've published. Now let's think logically about this. What if there was a game with no parent? Right? We'd call that an orphan record. Should that happen? Probably not. What would happen here if I tried something like that? I would insert the game, or I'd generate the game ID automatically here. I would insert Mario Odyssey 2. There's no Mario, is there? Not yet. No, okay, there will be. No, they don't usually go with sequels. They just do something completely different, right? All right, so, well, I guess Paper Mario 2. Galaxy 1, Galaxy 2, okay. But that was the swingy thing. What is it? Wii, there we go. Yeah, there we go. Anyway, now I lost my train of thought thinking about Mario games here. Anyway, I've got an orphan child here, and if I don't put in the publisher ID, if I put in the restriction that indeed this relation has to exist, as any good, well-designed database would, then that insertion of that record would fail. This requires a publisher ID. By the way, you can design databases that have a foreign key, but then that foreign key is optional. That would show up as an unfilled red diamond here. Right? Filling it in means that it's required. Down here, this is not filled in. This is not a required field. Right? So you could put in null for this. Okay. Anyway, we've got a parent-child relationship. A child cannot exist without a parent. So a child cannot exist, at least database-wise, without a parent. record, right? Can a parent record exist without a child record? Could we have a publisher that hasn't published anything yet? Yeah, sure. So if I were to insert data, what order do I need to insert it in? Insertion or creation. Publisher, the parent, and then 2, then I can enter the game data, right? Game. So publisher, game, right? Let's look at a more complex relationship over here. What is the relationship between game and platform? Well, I've got this other thing sticking in between them. Think about the real world relationship between a game and a platform. So now, unfortunately, here I'm going to have to go off Nintendo because Nintendo is exclusive to its own devices. Now let's go ahead and go with GTA 5. Right? Or the one I was talking about yesterday was the 15th anniversary, 20th anniversary that everybody's griping about because it's terrible. It's the definitive, okay, with absolutely terrible graphics, right? Anyway, let's talk about GTA Definitive Edition, right? What is it available on? PC, Steam OS. We're not gamers. I'm not either. Right? What else? PlayStation. All right, it's on PlayStation, Xbox, etc. So in other words, one game can be published on multiple platforms. Can be, right? Now Mario Odyssey is only going to be available on the Switch, right? But that's because it's Nintendo. What about one platform? Would it be a good platform if it only had one game? Probably not. So what relationship do I have between these two? A many to many relationship. A many to many relationship. To do that, I've created this thing down here called a join table. This is called a join table. Why? Well, because it joins two tables together. Right? We call things what they are, what they do. And it has two, remember these are called foreign keys. This is a foreign key. It refers to a key over here in a foreign table, right? An away table. I've got two foreign keys here. One of them refers back to the game ID in one table, and the other one refers to a platform ID over here in the platform table. So who's the parent and who's the child in this particular scenario? The game table is a parent. The platform is another parent. And then this one will be the child. All right? And same rules apply as before. Oops, over here. That a child cannot exist without a parent record, but a parent record can exist without a child. A game can exist without being published on any platforms yet, or available on any platform. And a platform can exist without having any games on it yet. Right? The Nintendo, not 3DS, what am I thinking? There was like a CD system that Nintendo put out a long time ago, and it had like one game on it or something. Okay, I don't remember what it was. It was a terrible, terrible Zelda game. Anyway, look up, horrible video game histories. Anyway, we've got a parent-child relationship here. This can exist. This can exist. But if I have an availability record, I need both of its parents to exist before I can say that it's available on that this particular game is available on that particular system. What about deleting things? The opposite, the reverse, right? Can I delete a publisher? Can I delete Nintendo out of my database? Well, lots of things might be referring to that parent, right? What if I just deleted the parent right here? Then I would have many orphaned children. Right? We don't want that. So if I do want to delete Nintendo, what do I need to do first? I would need to delete any game record that refers back to Nintendo. Well, before I do that, what do I have to do anything else? Delete any availability that refers back to that particular game. Do I have to delete any platforms? If I want to delete Nintendo and Super Mario Odyssey and whatever else Nintendo has published, Do I need to delete switch? No. Right? So there is a parent. From that perspective, what is this thing right here? It's the grandparent of the availability table here. So I've got a parent, child, and then that child has a child. Well, now I've got a grandparent up here. It's hierarchical, but it's hierarchical through its relationships. Okay. All right. Any questions on? Yeah, go ahead.
So, the publisher has the name attribute which game has,
Mm-hmm.
but availability doesn't have the name attribute. But
That's because it's normalized, right? So what? Give me a name.
Mario.
All right. So that name would be associated with the game, right? Now give me what Mario is available on Switch, right over here. Right. Does Mario and Switch need to be in here? Nope. That's stored in one place and one place only. It's all the problems that I had before with redundancy of repeating this string over and over and over again. Now I'm not repeating it anymore. I am repeating the keys, but that's okay because I do need to refer back to it. But if I ever change the name, I change one record in one table. I misspelled Nintendo, Nintendo, right? And I need to add an N to it. Instead of changing dozens and dozens and dozens of records, I change one column in one table of one record. Right? And it's effectively changed for all the records that refer back to it. So that's what normalization refers to, that you are separating things out, limiting and reducing redundancy or eliminating it entirely, and then defining relations so that you don't have those potential failure points anymore. Yeah.
So when you're creating a database, is there like a specific syntax you have to follow?
SQL, yeah, and it's we've got enough time. We can look at it. So if you choose to do Lab 15, you can take a. We wrote all the code already for you. You don't have to write any SQL. You don't even have to write any ODBC or JDBC. We did it all for you. Let's go ahead and where is it going to be? Game? Nope. List games? Nope. Insert game data ODBC utils. No. Where probably games.c. All right, there we go. So here's a piece of SQL. Right? Insert into game, and then here's the basic syntax: game, the game table, the column name, the other column name, values, and then I put in question marks here because those get set down here. Right? It protects you against what's called an injection attack. We'll talk about that in computer science too. Right? But otherwise, that's what SQL looks like. Inserting, where's find, select. All right, there we go. Select star from game, select all game records from the game table. So that's what SQL looks like. Now, all this other stuff around here, this is all ODBC. This is code for actually connecting programmatically to a database using C. If you want to look at what it looks like in Java, that's going to be JDBC, Java Lab 15. And you can use this because it ships with the correct jar file to get things done here. So you can go ahead and do this on your own ID and on your own computer. But what does it look like? Oh, here, I've got the actual SQL. This is how I created the database. So how do you create tables? There you go, create table. How do you insert data? There, I inserted a bunch of publisher data there. It's all just test data. Create another table for the platform. You label, the columns here. You label the primary key. You can define foreign keys and the table that it references, and then the column in that table that it references. So it's just another language. It's SQL structured query language.
Are we going to be using query in the next class?
Oh yeah, definitely. You will design your own database. You will insert records like this, and then you will write JDBC code to connect to the database and pull and do a report. Yeah. But yeah. if you over the break, if you want to, I've got videos on it, just like I've got videos for this course. All right. So, highly recommend that you get involved with Corn Hacks. Again, that's going to be UNL Corn Hacks, was it? .com. Maybe that wasn't it. Okay. They just paid for a cheap machine, maybe. It's not that. It's probably just my connection. 50 days from now. So in January, I don't think she mentioned it, but you've got that first week of class, and then it's the weekend after the first week of class. So it's before, your semesters get really busy. And it's a good, it's fun time. Go ahead, and I recommend that you sign up for it. I may or may not be judging, I don't know yet. Okay. No questions online from YouTube, so have a good weekend. Next week, we will devote the entire week to review. I will bring old final exams. We'll do as many as we want. Otherwise, remember that you can also check out, I'll also do, Advent of Code. It opened up as of yesterday. Now we've got day 2 as well, because today is December 2nd. So if you want some nice, simple exercises for code, kata, or whatever, then I highly recommend that as well. All right. I'll see you next week.